In this video I'm going to explain simple resistive networks, that is series resistances and parallel resistances. And we derive these fundamental principles of series and parallel resistances, so two resistors in series and two resistors in parallel. We derive the equations from Ohm's law. So, first of all, before we start, think you were this voltage source, right? And what would you see? At this point, you have a voltage drop, V0 coming from the source, and a current running through this circuit, right? So the current I leaves the voltage, runs through something, and the same current then enters the voltage source again. The same is happening here. So we have we have parallel resistors here. So the current leaves the voltage source, and here at this point, at this junction, at this joint, the current splits, but then merges again, and it combines to the same I again, right? What goes in has to come out, and it goes back to the voltage source. So this means that in the end, you have a voltage source, you have a current leaving the voltage source, running through a resistor network, and the same current is then entering the voltage source again. And the same is happening here, right? Okay, so what in fact is seen from outside is this. You have a voltage source, a current, a resistor, the same current, and back to the voltage source. And the same is true for the parallel resistances, right? So from outside, you really don't have to know what's inside this big resistor or effective resistor R. Same as here, right? From outside, it's only interesting to look what the resistance R is to find the relationship between V, I, and R, right? So we can definitely say, according to Ohm's law, that V0 is R times I. And it's this R, the effective resistance R we have here. And the same is true on the right side. V0 is R times I. So now let's have a closer look here. You see that in the case of the series resistance or serial resistance of two resistors R1 and R2, the current is the same through both resistors because there is no junction here where the current could basically be split. So that means I coming from the voltage source is the I running through resistor 2, through resistor 1, all the same current, and then going back to the voltage source. And you can see that we have a potential difference here coming from the voltage source. So let's say, for example, plus 5 volts. So this potential might be 5 volts higher than that one. And we define this to be 0, but this is just when we do calculations. And we want to convert everything to absolute numbers. So we need a reference potential. We could put it everywhere, and the results would be the same, right? You would come up with the same resistance, for example. But it's convenient to choose a point which is connected to the negative terminal of the ideal voltage source. So in this case, I'm using the symbol for an ideal voltage source. Okay, so we have a voltage, so a potential difference here. And the potential difference is basically a difference in potential energy. So we have a higher potential energy here than here. And now, since currents are running through these resistors, they lead to a voltage drop, right? So that means we have a potential drop. So we start at some potential here, and then this potential gets lower at this point, and then the potential gets the lowest here. So that means we have two drops in the potential because this voltage drop or we call this potential drop in potential. And it's since energy has to be conserved, right? We have a potential energy here, and we are dissipating it, right? So in this resistor and in that resistor. So that means the energy has to go somewhere. That means the total energy drop is the sum of the energy drops in the individual resistors. So that would be V0 is in the end the potential we start with. Is delta V1 plus delta V2. Okay, so how large is the voltage drop across this resistor? So we have here the potential V0. Here we have a different potential at this node. There is a different potential. That would be, this potential at this point would basically be 0 plus this voltage drop here. That would give us this point. So what this resistor R1 sees is a potential difference from this point to that point. So from some intermediate potential, what could I call this? Maybe potential, let's call this potential V1, why not, right? So this is the potential V1, and here's the potential 0. So this potential difference is delta V1. And this potential difference leads to a current through this resistor R1. So that means delta V1 is R1 times, what is the current through this resistor? We said before that the current is not bifurcating, it's not split, so it's the same everywhere, which means the current running through resistor R1 is I. And this I causes, together with this resistor, this voltage drop, delta V1. So, and the same holds, of course, for delta V2. It's the same, right? The same current now running through the resistor R2, causing a voltage drop V2. And now the system balances in such a way that the total voltage drop, right, is the sum of the individual voltage drops across the resistors, is then R1 times I plus R2 times I. And now we can factorize I, which is R1 plus R2 times I. Okay, but what is this R1 plus R2 times I? If you look from outside, V0 is R times I. But V0 is also R1 plus R2 times I. Now if you compare the coefficients in front of the I, they have to be identical, which means that on one hand V0 is R times I, on the other hand V0 is R1 plus R2 times I. So in the end it follows that R has to be R1 plus R2. So this is the formula for the series resistance. So to derive this formula, you simply have to take into account that the current is identical, the voltage drops are different, and we are applying then on one hand the law of Ohm, and on the other hand the conservation of energy. This is the conservation of energy. Energy conservation. Okay, now let's have a look at the series resistance. So obviously the current, so the electrons for example coming from here can decide whether they go through R1 or they go through R2, right? So it means the current is basically split. So part of the charges run through R1, part of the charges run through R2, but in the end they are combining again, they are merging again, and sum up to I again. You are not losing any electrons in between. This is you can say that this is the continuity equation. So I is I1 plus I2. This is the continuity equation of charges, right? Your conservation of charges. Charge conservation. We call this a continuity or a conservation equation, right? So you are not destroying electrons while they are roaming around. Good. Now, let's have a look at this I1. So the current running through resistor 1 is the voltage drop across the resistor 1 divided by resistor 1. So, but what you can see when you compare these two nodes, these 2 points here, they share, so they define the potential difference across the resistor R1, but also across the resistor R2, which means this R1 sees the same potential difference as the resistor R2. So the potential difference driving the current I1 through R1 is, in fact, delta V. So that's this delta V is driving the current I1 through resistor R1. But the same is true for I2. It's delta V divided by R2. So now let's sum. So let's substitute the currents in the charge conservation equation. So it follows that I is now 1 divided by R1 plus 1 divided by R2. So I'm now factorizing this dV, right? So and if you compare this, this is equivalent. If you go to the initial, so now when we observe this thing from outside, we see just this effective resistor. So forget about the internal structure of the resistor, right? What we see from outside is just the current and the voltage drop across this large structure. That's this formula. And let's solve this for I. I forgot to mention, of course, that the voltage drop dV here between these 2 nodes, you see that it's the voltage drop or the voltage of the voltage source, of the ideal voltage source, right? So let's see. Let me take these 2 pens. So here we have a potential of, let's say, plus 5 volt, here 0. So and you see there is nothing in between which changes the potential. So the potential is still the same, right? So when you go here for an ideal conductor, you wouldn't have any voltage drop, any potential drop. So the potential here is the same as the potential here, right? Because we have ideal conductors here. Good. That means this V0 is in fact also the delta V0. I can write it down here. So that the voltage drop across the resistors is identical to the source voltage. Good. So now if you compare now these equations, you see on one hand we say, okay, 1 divided by R delta V. So when we look at the, oh, where's my resistor? Is here. So when we look at the total system from outside, I is 1 divided by R delta V. When we look more closely, we say I is, in brackets, 1 divided by R1 plus 1 divided by R2 delta V. So and again, we are talking about the same current, we are talking about the same delta V, which means it follows that 1 divided by R is 1 divided by R1 plus 1 divided by R2. Okay, so this is series resistances, and this is parallel resistances. Parallel resistances.